Yeah, welcome everyone to day two. Today we'll be finishing our thing on regression, which we started the slides on yesterday, and then we will be moving on to classification, which we'll be doing for the remainder of the course. So we'll start by doing this code for regression. We'll have some slides about classification, and then we'll create our first, or I guess, artificial neural network for classification. We're about to create one for regression. So if you haven't already, go to the Deep Learning Files channel, and I put a data set there called King County House Data, which is a county inside of near Seattle, Washington, I think, or and it's just house data that's from that area. But for those who do have it, we'll just go ahead and start importing our standard libraries. Import pandas as PD, import numpy as np, matplotlib, import seaborn, and then last but not least, from google.colab, import files. All right, and then we will go ahead and upload our King County house data. And then we will read it into a pandas data frame while that's loading. df equals pd.read CSV. And this is called King County House Data .csv. And we will run df.head on that to take a look at what we have. And I'll give everyone a second to catch up. Oops. I wrote country. All right, I'll give everyone a second to catch up. Let me know, or I guess I'll throw up a poll to see when you guys are ready to go. Have you uploaded the data set and put it in a data frame? Yeah, it is. Some of these are pretty expensive, and we'll be able to create a pretty cool scatter plot that almost creates a map as to where they're the most expensive. It'll be pretty insane. All right, we have, how many thumbs up is that? All right, we have thumbs up all around. Nice. Let's move forward. Okay, so let's take a look first at the data that we have, right? That's the most important step right at the beginning of every process. We have the ID, which doesn't really, it's not really useful to us, right? We don't really need it to analyze any sort of correlation or anything. It doesn't mean much. It's just some sort of ID that's tagged onto these houses that are for sale. We have this date. Now this date looks very strange, right? You can kind of see the year here, 2014. Then maybe that's the month and the day. And then there's this T000. So it looks like we're gonna have to fix this in order for our model to actually understand what the date is, right? This doesn't look like a date to me right now. It is, but it's just formatted very strangely. Then we have the price. This is going to be useful. What you can probably imagine is that what we want to do is create a neural network that takes in all of these things into consideration: bedrooms, bathrooms, living, so on and so forth. There's a lot of things here. It wants to take all of these things into consideration in order to, well, predict a price, right? So our price is going to be our dependent variable, and all of these other things are going to be, I guess, our independent variable, or the training data that we're trying to match a label or a price to it, right? And this is regression, so it's continuous. We can predict any value, the specific number of any value, I guess. So we have a lot of neat columns. Go ahead and scroll through all of these. We also have a zip code column. That's not going to be very useful to us, right? Because a greater zip code doesn't mean a more expensive house, right? There might be a correlation within zip codes that one zip code is more expensive than another. However, it's not in the same format, if that makes sense. Like a greater square foot house will probably cost more. However, the zip code thing is probably something that we don't want to consider because it's not going to help our model very much. So let's go ahead and start checking for if there's any missing data. That's the first step that you should do in any data set. Who remembers the command for that? Yeah,
df.sum.
What?
df.sum.
Close. df.sum will just count up all the numbers. The question was finding all the, I guess, missing data inside of the thing for Shri, who asked if I could repeat the question. Finding all the values. The df and then the dot sum, they're both part of it, but there's something in the middle, in between df and dot sum. It looks like df dot blank dot sum. What are missing values called? I guess what's another term for them?
Wait, df.isNull.sum.
Yep, yeah, perfect. So isNull.sum. Nice. All right, so we will do df.isNull.sum. It's pretty common practice to just do this at the beginning of any data set. And especially when we're working with neural networks, because if we have missing data, then our neural network will run into some sort of issue because it's expecting numbers everywhere. And it can't read in these null values.
This one actually has nothing that's not there.
Yeah, so it's a very clean data set. Everything has been done nicely for us, and we have no missing data at all. So that's very good. That makes our life a lot easier, and I chose it for that reason. I feel confident that you guys can look back at the code from Python for Research and fill in the null values if need be, or remove them. So let's not get caught up by that and just move forward since we're all good. All right, let's move into getting some summaries. So df.describe, and then who remembers the command that we use to take like I guess we can run this df.describe, but if you see it is very wide. Who remembers how to turn it to be lengthwise? Like flip the rows in the columns.
.invert.
.invert, that's a good guess. Just a synonym for it, .transpose.
Oh yeah.
Yeah, that's a very good guess though. Similar word. Oh, and Noah just joined us. Actually, I'll get him up to speed. We're only a couple lines of code in. Noah, go ahead and create a new Colab notebook and download the CSV file inside of Deep Learning Files, and let me know when you have that ready. All right, but in the meantime, let's take another step forward. So who remembers what the command for a histogram is inside of Seaborn? A hint is that it's not called sns.histogram. Actually, you know what? Let's scratch that. Let's take a look at this. Let's take a look at this table first. It's not .history. That's a good guess, but it's not called. It doesn't have anything to do with hist, I guess. All right, but let's start by looking at this table that we have here, right? We've printed it out. Let's also take a little bit of a look at it. So it's printing out, I guess, the number of data points that we have. Looks like we have data for 21,613 houses. Pretty respectably sized data set. She said dist plot. Yeah, that's exactly right.
Okay, I have the CSV down.
Okay, cool. I'm gonna go back. You guys can keep taking a look at the table in the meantime.
Wait, so what exactly does the dot describe function do? Does it just like looks like it's just doing exactly what the dot read did?
Well, take a look at the row or the column headers. Is it just printing out I guess, the features?
Oh wait,
Or-
oh no, I just noticed that.
Yeah, it's printing out a lot of summary statistics. So that's what these are for. Yeah, Noah, you can just go ahead and copy these lines of code down. We're importing our standard stuff, loading in the CSV, very, very classic things, and then reading it into a CSV. Let me know when I can scroll down. But yeah, you should notice like the 25%, the 50%, 75%. Do you remember what those are called?
No.
Think about box plots. What is each of those sections called? Each
Oh,
section.
those like each quartile?
Yeah, each quartile. Perfect. So the 25% is the first quartile, 50% is the second quartile. What's another name for the second quartile or the 50%?
Interquartile range?
The interquartile range is the 75th quartile minus the 25th quartile. The 50% mark, or that middle line in the box plot.
median?
Yeah, it's the median. Yeah, nice. The IQR, the interquartile range, is Q3 minus Q1, which is the 75th percent number minus the 25th percent number. Then we also have standard deviation. What does standard deviation describe inside of a data set?
The average difference between each answer?
Yeah, perfect. It's the average, the average, I guess, spread from each data point to the mean. So yeah, I'm really glad you guys remember a lot of this stuff. Noah, are you good on this?
I'm on the pd.read.
Okay,
df
cool.
equals pd.read.
We'll give Noah a second to catch up, and then we can scroll down. I think he only has like 1 or 2 lines left, so we should be good. Yeah, and then once you had the data set, basically what we're going to try to do, Noah, today is take all these features of houses, such as bedrooms, bathrooms, living square footage, lot square footage, whether or not it's on a waterfront, and we're going to try to use those to feed them into a neural network and predict a price. And down here, the df.isNull.sum, that's just seeing if we have any missing data, if you remember that command. Are you good on this?
Yeah, hold on.
So wait, I'm sorry. The second 50% quartile, that's
Mhm.
just like the median, right?
Yeah, it's just the median. It's 50%. Yeah.
There is not really a second quartile, right?
Yeah, well, the 50% is the second quartile, but people just call it the median. No one ever calls it the second quartile.
Oh, okay.
Yeah. But it's the same thing, right? Second quartile means 25 and then 50% in, right? If you have 2 quarters, you have 50 cents.
Yeah.
Which is the same as the median of $1.
df.is. All right.
Okay, cool.
I did the df.isnull.
Yeah, and when you run that, you should see zeros across the board, meaning that it's a very clean data set and we don't have any missing data.
Okay.
Now what we'll do is do df.describe.transpose. Since everyone else has looked at this already, I'll just let you write this down and look at it later. But we will, once you get this done, we'll move on to the next section of the code.
Oh, I forgot that little parentheses. There we go.
All right, got that down?
Oh, are these the different columns?
These are the summary statistics for the df.describe, such as the count, which is the number of data points in each column, which they should be
Yeah.
the same, right? Because we had no missing data.
Yeah.
Then we have the mean, we have the standard deviation, then we have our min max, and we have all of our quartiles, which if we were to create a box plot out of the data, we would
Yeah.
see these values on the box plot.
Then there's the maximum. Okay.
Yeah, and max. All right, so let's go ahead and yeah, Shri got it. I asked how do we plot a seaborne histogram? I said this plot, so that's perfect. Let's go ahead and let's make a little bit of a larger figure. So plt.figure fig size equals 10 by 6. And we're going to do sns.distplot, distribution plot. And we're going to plot the price on this one. So df of price. We're going to take the price column from our data frame. All right. And we should have a plot that looks something like what's kind of on my screen here. And the reason that the price is in like 1, 2, 3, 4, 5, right? Because if you look at the very right of the plot, it says 1 e to the 6th. Have you guys learned what the e means in math? No? It's basically like, you can think of it kind of like scientific notation. It's times 10 to the 6th. So 1 e to the 6th is 1 followed by 6 zeros, which is what? 1 million. So it looks like most of our houses, they're clustered around 500,000 in this region, it seems like. About halfway between 0 and 1 million. And
Wait, can you scroll up again?
What?
Can you scroll up to your code again?
Yeah.
So I forgot exactly, what does fig size do?
It just changes the size of the figure. It's just figure size. And this is width by height, 10 by 6.
So it doesn't have anything to do with the scale of the figure?
Well, if your figure is too squished, then it will I guess no, not the scale, but the appearance, yes. Like if it's squished horizontally or vertically.
Okay.
Yeah, like if I were to do 2 by 6, it would look very strange. Yeah, if you see this here, looks quite odd, right?
Mm-hmm.
The scale is the same, but it just doesn't have enough space for all of those tick marks. But yeah, good question. Let's keep it 10 by 6. And so I just said 1 e to the 6th is the same as 1 followed by 6 zeros. I think you can actually just type that into Python if you ever forget. Yeah, if you ever forget, you can literally just type 1 e to the 6th and run it, and it'll like print it out for you. So it's pretty nice, to be honest. And it seems like most of our houses are clustered or at around 0.5 e to the 6th, right? So let's go ahead and see what 0.5 e to the 6th is. So we have about 500,000, right? 500,000. And let's actually go ahead and kind of let's confirm that and look at our price. And here we have it. Looks like we're at about 5.4 or 540,000. So it looks like our histogram kind of confirms this idea that we have in our summary table.
So wait, what's the +5 afterwards? +05 or +09 afterwards?
That means how many zeros there are after it. Or like how many places you move the decimal over, kind of. That's what the E is. So
So
if we were to take this decimal and we were to hop it over 5 places, that would be our value. It's kind of like scientific notation.
Oh wait,
Yeah.
so that plus 0.5, is that the exponent to e?
No, it's how many places you move the decimal over.
So I'm confused then. What exactly is e?
It's like scientific notation.
It just is it not does it not have any numerical value?
No, there is. It's not to be confused with the variable e, which is like 2.71. It's like Euler's number. It
Yeah.
should be a capital E, like on your calculator. If you were to take your calculator, there's a button that says like there's a capital E, and if you do 5e to the like 10th, I can't really fit it in the camera, but there's if you do 5 on the TI-84, it's like second comma, and there's like 2 E's there, even though it just prints out 1 E. Yeah, what Sri put in chat is correct. It's like 6.5 times 10 to the 8th, or in this case, it's 5.4 times 10 to the 5th. That's all it is.
Okay, because I thought it was Euler's number being used here.
Yeah, no, it's not.
No.
It's not to be confused with Euler's number.
So it's
which
just
is what-
okay. So it's just scientific notation.
Yeah, it's just scientific notation. Yeah, sure, exactly. 6.5 times 10 to the 8th is the same as 6.5 E8. It's actually pretty useful in high school math classes. It's much faster than typing out times 10 to the 8th. You just put an E and then you put the number you want after it. Yeah, and you can create your own little calculator by simply typing the command over here. All right, so let's go ahead and create a count plot of the bedrooms to look a little bit at the data. And it looks like we're just at about three bedrooms, looks to be our mean and our median. And interestingly enough, this shape over here is pretty similar to the shape that we had above there. And it looks like some absolute legend has a 33 bedroom house, and they had to like create the scale to fit this guy's massive house. I don't know. But yeah, what a legend, I guess. I don't know who would need 33 bedrooms, but I guess there is a guy. I mean, the data indicates that, but all right. Let's go ahead and now do something that we actually have not learned in research before, but it is very important for neural networks. It's to look at the correlation between different variables. Yeah, I can go up a bit. It's to look at the correlation between variables and how much they impact price, if that makes sense. So the higher the correlation, the more they play a role in determining the price, right? You would imagine that your square footage is probably your biggest contributor to the price, right? And then after that, some other things might come into play, but let's go ahead and see the correlation between each variable. df.corr, and we want to see all the variables that are correlated with price. So we do core with the column of price, and then let's go ahead and do sort values. So that way it sorts it from least to greatest, so that we can look at the highest correlation at the bottom instead of having to like manually check. So let's run this. And very cool. So if we look at zip code and ID, remember I said that those are probably like pretty useless, right? Like the ID is just some random ID assigned to the house, and the zip code probably doesn't play it doesn't play a correlated factor with the price of the house. A bigger zip code doesn't mean a bigger house price, right? It's just different people have different priced houses in certain sections of it. So it looks like these are actually negatively correlated, or I mean, at this point, they're just randomly correlated. They're not correlated at all. Looks like the longitude has about a 2% correlation, pretty bad, right? The condition and the year built have 3 and 5% correlations. Looks like it's pretty bad, but let's look at some of the top couples. So let's look at price. Obviously, price is 100% correlated with price, right? That you can kind of ignore that because like that's basically like saying A is equal to A, right? That's obviously it's 100% correlated with itself. because each price is the same as each price of itself. So hopefully it makes sense why this is 1 or a perfect correlation. But now we have some pretty high correlations up here. We have living square footage. I don't know why there's a 15 after it. I didn't really read about the data set too much. But we have square footage above. We have the grade of the house, which I guess is like the quality or maybe the type. And then we have living square footage, which is 70% correlated with price. So looks like the square footage of the house, or the living space square footage of the house, plays a huge role in determining what the price is. In fact, it has a 70% correlation with it. So we can kind of see that the neural network is going to assign basically like a higher weight in order to kind of consider this as a more important factor. We're actually never going to tell it that, hey, this is correlated very highly, but by itself, a good neural network will figure out that these top couple of things have a much bigger say in determining what the overall price of the house is. So pretty cool that we're seeing this manually. We're seeing this manually, but the neural network should pick up on that pattern if it's decent.
Wait, so the dot core function,
Mm-hmm.
so that just, how does it determine these numbers? Does it just look through all the data and does it just like run calculations that we just don't get to see?
Yeah, no, it's actually, well, it is running a calculation, but it's simply looking at the like correlation between each of the variables, I guess. Let me Google how you calculate. How is correlation calculated? It's not very math intensive. That's why it does it in just a second. Yeah, so it uses a lot of the standard deviation stuff that we talked about it, and it basically it takes the standard deviation from both of the variables and kind of divides something that's known as the covariance. I won't get into that, but you can think of it like the variance, I guess, when you're comparing two separate variables with each other, and it just simply uses that. It's just a very quick, almost real-time calculation that it's able to perform to look at the correlation. It's just you use it a lot in like investment, and yeah. Let's see if there's a formal. Yeah, there's not really a formal formula. Some people use different things. I'm not sure what Pandas uses specifically, but there's a lot of ways you can calculate correlation. But yeah, good
I was
question.
just curious where the number came from. It was like, it came really fast and it seems got accurate information for all of them.
Yeah, it's very computationally cheap, I guess, and it plots it on a range from -1 to +1. -1 being like negatively correlated almost 100%, like it's the inverse of the actual data. So if we had a new column called like negative price, it would have a relation of -1, right? And then the others, 1 is 100% correlated basically. So every data point, if we were to plot it on a line, it would just be a straight line. All right. Let's go ahead and move on to, let's see if some locations have a specific, I guess if they're more expensive than other locations. And I think this will be very interesting. So how can we create a map, I guess? How can we create a scatter plot map of all of these data points? Does anyone have any ideas?
Of all the data points of all these percents?
Yeah, so basically, let me actually,
Oh,
not of all the percents, just plotting them on a map to basically take these data points. You might have to look at some of these column names and see how
well, I
can
mean, like, there's zip code.
zip
that
code
would
is
be
a good
really-
idea, but will zip code give you like something that looks like an actual map? Because a zip code is just a region, right? We want a specific location.
It would be the ID then.
The idea is just something that's randomly applied to all of these houses, I guess.
Longitude, latitude?
Yeah, longitude, latitude. Let's take a look at what King County looks like. I have a picture of a map. And yeah, let's actually create something like this where we're simply constructing this map, but based off of the scatter points that we have with us. I'll bring this map back in a second. Let's create a little bit of a big plot. Let's do plt.figure. Fig size equals 12 by 8. And let's do sns.scatterplot. And x equals longitude and y equals latitude, right? Because latitude is going up and down, longitude is going left to right, or I guess east to west. Left and right, that's a horrible way. Don't use that to describe latitude and longitude.
Is that SCS?
Oh, shoot. Thanks for catching that
Okay.
typo. That should be SNS. Theta equals DF. All right. And what Noah said about zip code will be pretty cool, actually. If we were to sort these points by zip code, I think that would look very nice. We can actually try that. I didn't have that planned. Yeah, let's take a look at this. This looks like, well, it looks very close to, or it looks exactly like our, I'm going to minimize this a little bit. And yeah, let me just open this map of King County. Oh, looks like I got it in a new window. You should be able to see the similarities between this. So look at what we have here. We have this is the same as this little, I guess, water area over here, right? That's the same as this water area over here. This is Mercer Island, which is a pretty famous place in Seattle. But yeah, we've just taken this data and we've just put it on a map almost by just plotting the latitude and the longitude, right? Here it looks like we're getting into this territory down here with this cluster of data over there. And yeah, just pretty cool overall taking a look at Mercer County. So if we wanted to color these points by,
Thank you, Mom.
if we wanted to color these points by zip code, how would we do so?
Oh, I forgot what it.
Think about how we colored the iris data points by type of flower.
I forgot what it's called. What we did last time.
You can take a second. Shri got it. He said hue. Perfect. So let's go ahead and copy this code we have over here. Let's paste it into a new cell. And let's now add a new keyword argument called hue equals, and I guess we can do zip code first. I don't know if this is going to yield something interesting. I didn't test this out beforehand. Oh, it does yield something very cool. Take a look at this zip code thing. But yeah, you can see it kind of sorted by region, right? It's a little bit strange because it's trying to plot a heat map. So like higher regions have higher, or darker regions mean they have a higher zip code. But yeah, pretty cool nonetheless. Let's go ahead and make this by price. Shri is ahead of the game. Let's do it by price. That was my original plan. And if we plot it here, very interesting, right? If you look, where are the highest priced houses clustered around, more or less?
The water.
The water. They're either on the island or they're right next to the water. And that island, it might have been a little hard to see on the map. It's this little like coffee bean shaped area down here. But yeah, very, very interesting. So it seems like if you remember taking a look back at our data, we actually have a variable called waterfront. It doesn't have a high correlation, but it's simply a 0 if they're not next to a waterfront, and it's a 1 if they are next to a waterfront. So it looks like some of these houses that have a waterfront will have a higher price. But pretty cool graph, right? We've literally created a map and almost created a heat map that's showing us that people next to the water probably have a more expensive house price. I thought this was just a cool map overall. Let's move on. All right, so let's remind ourselves of what the data looks like, df.head, just so that we have it for reference. And now what we're going to do is something a little strange. Remember how I was talking about that this date is horribly formatted? Well, we want to do something about that. So I'm gonna use a lambda command. For those that are in Intro to Python, you learned about it. If you're not, don't worry about it. Look at it later. It's basically a one line. It's like a one line unnamed function, basically. Um, yeah, if you don't understand this code, don't worry about it too much. All I'm doing is creating columns that have the date properly formatted instead of this very strange like medley of all the dates followed by T and what is that, 6 zeros. To be honest, I'm not even sure what that T and 6 zeros means. But let's just get rid of that. All right, so Pandas has a nice thing called toDateTime. So it takes a date column and it converts it to something that can be split apart, which is actually pretty powerful. It automatically recognizes the month and year format inside of any date column formatted similar to this. So let's create a df month. Let's create a new column called month, and let's take the date. And what we want to do is apply a lambda function. So we do dot apply lambda, like the Greek letter, and we do lambda date equals date dot month. And once you have that written down, you can just copy paste it and just replace month with year.
Shouldn't it be date equals or is it date colon?
It's date colon. It's like when we were doing x colon x to the power of 2 for the square lambda function in Intro to Python, if you remember that. Yeah, it's basically like applying, this is like the type of function, and it's applying it to the date variable, I guess. Yeah. Lambda
Okay.
functions are pretty strange, to be honest, but they're very cool in terms of being able to simplify your code a lot. When I was doing my internship, they challenged me to write or to fix whatever the bug I was looking at in one line. So I just used like a really, really long lambda function and was able to squeeze it all in one line to fix it.
Why is it called lambda of all things?
That's a good question. I don't know. Lambda is just a very popular Greek letter. I don't know. Let's look that up. Why is it called a lambda function?
It's used to introduce anonymous functions,
Yeah.
according to Wikipedia.
Yeah, but that's not like an answer, I guess. I guess it's just a variable name. Doesn't seem like there's a clear answer as to why they chose lambda over other. Yeah, it doesn't really say why they're called lambda over some other Greek term. I guess someone just did it and they ran with it. But once you've gotten this, you can go ahead and run it. And now if you take a look at your data frame, at the very right, you should have two new columns, one called month and one called year, where it's extracted the month and year from our date, from our original date column. All right, so now let's get into the neural network stuff, finally.
Wait,
Wait, hold on,
I
I got
don't
an
have
error.
2 new columns.
You got an error.
Yeah.
What does it say?
str object has no attribute month.
str object has no attribute month. Did you make sure to put the underscore in between toDateTime? Or
Yeah.
put a screenshot for whoever's having an error in the chat.
Whoops, I'm posting it in announcements.
All right. That's fine. We're not really very strict on these. Announcements, PD, toDateTime, that looks good. dot apply, date dot month. Looks good. Df month equals df date dot apply lambda date. That looks good to me.
Wait,
I don't see anything wrong with it. Should I just copy my code into the chat and you just paste it in? I don't know if it's like a minor typo.
I guess.
It looks
Hmm.
exactly right to me though.
Let me just.
Is it working for everyone else?
I see what he did wrong. He
Okay.
said date colon date dot month. It shouldn't it be data dot colon data dot month?
Data?
No, I mean, for me, I just put date, colon,
Yeah, it should
date,
be.
month.
Oh, yeah, in the very first line you put data instead of date. I think that's what Shreyas was saying.
Oh
Oh,
yeah, sorry.
Yeah, you just flipped it around. Yeah, no, that's good catch. I did not see that.
oh, thank you.
Thanks, Shreyas. All right.
Thank you, Sharon. It's very cool.
Let's go ahead and create our x and y variables now. So let's have x. So remember, x is what we're going to train the model on, and we want to have y. Y is going to equal the price. So what are some of the irrelevant columns that I said that we need to get rid of when we're trying to determine the price?
ID.
ID.
Yep, ID is one of them. We have 4 in total. Actually, another one is date, because we only want to use the month and the year, right? This is not the 2014-10-3 is not a format that's readable by a neural network, obviously. It has a bunch of dashes in it and won't make any sense. So we have 2 more. What are 2 more?
Zip code.
Yeah, zip code. Remember, it was negatively correlated, which is the same thing as being randomly or basically harming the model. And greater zip code doesn't mean a higher price, so it's going to negatively impact our performance. And this one is a trick question. What's the last thing we need to get rid of?
Longitude, latitude.
No, that actually does play a role in it. If you remember whether like its location, some locations had a
The
better.
condition.
The conditions.
Year renovated.
Year built.
Nope. A hint
I'm
is
just
that
throwing
it's.
stuff out there.
Yeah, you guys are just reading off. Let's look at the y data. Let's leave that alone for now. What did I just say the y was going to be? What is the dependent variable?
Price.
Yeah, price. And we're going to do dot values. That converts it to a NumPy array to feed into our model. So if the price is the y variable, then what do we need to get rid of from the x variable?
Price.
Yeah, price. We can't feed price into the model, right? That doesn't make any sense at all.
Okay, that
So,
makes
yeah.
sense.
yeah, so we have to get rid of it. And remember, we have to do axis equals 1 whenever we're dropping columns. Axis equals 1 dot values. All right, so now x is a nice NumPy array given by the dot values, filled with all sorts of things other than the ID, which doesn't make any sense, the date, which is simply not readable, the zip code, which doesn't make any sense either, and the price, which is the answer, right? We don't want to give it the answer. So think about what we're doing in model training, right? We're giving it unlabeled data by dropping the price out from it, if that makes sense. But we do have the labels, and the labels are stored inside of y. Let's run that. Now what we need to do is import train test split. You remember how I was talking about we split our data into 3 data sets? For our first neural network, we're just going to split it into 2 data sets, training and testing, actually for this one and the next example, and then after that we'll start splitting it into 3. But for simplicity's sake, right now we're just going to explore the syntax of a model. So let's just, from sklearn.model_selection, import train test split. Get used to this because train test split is going to be used forever every time you create a neural network. And now it actually, train test split returns a really nice, I guess, 4 variables for us. And those 4 variables are x train, right, which is our training input data, our x test, which is our testing, I guess, all these quantities.
Wait, should we write this?
Yes, you should write this, definitely.
Okay.
We're going to be creating our neural network and feeding all of this stuff in. Y train and Y test. It looks a little strange. That's because the train test split returns 4 variables, and those 4 variables are the X training data, the X testing data, the Y train, and Y test, which are our labels. So now what we can do is pass in X and Y, right? We want to pass in the labels that, or the data that we want to split. Now, what else do we need to do when we're splitting our data? If you remember the diagram from the slides, there's something else that we have to specify while we're splitting data.
Do the X's need to be capitalized?
Yeah, it's like convention to do so. They don't need to be, but like it's like, I guess in data science people usually do it just because X often gets used for other things as well. So capital X is usually the independent variable.
Right.
So we have X and Y, and we know that we're going to split these, but what is missing from our arguments? We know that we're going to split these, but what's something else that the train test split needs to know?
How many times?
How many times? I guess
It's
kind of
split?
sort of on the right track. Like how much is split? Remember I had like a couple
Oh, the
proportions.
percent.
Yeah, the percents. So I had a couple proportions that we could try. So yeah, pretty close to, I guess, how many times it's split and just, I guess, how much it's split by. So all you have to do that is test size, and then you specify a percentage. So let's do a 70-30 split here. We don't have a validation set in this example. We just have a training set and a test set. And our test set is going to be 30%, and our training set is then obviously it's going to be 70%, right? And just so that we get the same numbers, let's do randoms. Let's all set the same random state, and let's set that to be equal 101, just so that you and I get the same exact random numbers. If you remember what pseudo-random was from the research.
Wait, so for the test size, how does the split affect like the data?
So basically what we do is we have a NumPy array filled with around, what was that, 21,000 values in it. And it just like takes 30% of them and then just reserves them for the test variables, Y test or X and Y test, if that makes sense.
Oh, okay.
Yeah, it's just like, I don't know why, but I keep using the example of the loaf of bread in these last 2 weeks. And you just take 30% of the bread and you just save that for the test data sets. And you train with the rest of it. All right, so now what we have to do is import min-max scalar. If you remember from the regression lesson, min-max scalar basically just turns all of these values into a number between 0 and 1, depending on their proportion and their standard deviation and so on. So we always have to scale the data. And you can use other types of scalars. I don't think it affects it, but I like min-max scalar.
I got a syntax error.
For which part? The train test split?
No, for the import sklearn.preprocessing.
Oh, it's from sklearn.preprocessing. Import min.
Oh, okay.
And then we'll create a new variable called scalar equals min-max scalar. So now what we have to do is 2 things. We have to fit and transform our training data according to the scalar, and then we have to transform our data to the X test. Yeah, I kind of sort of forgot what this actually means, but I just remember that this is the steps. I'll look it up before next lesson and re-explain this. I just know that you're supposed to do fit transform to the train data, dot fit transform to the train data X train. So we're just standardizing it itself basically. And then to the X test, we're going to do the same thing, except it's scalar.transform and not fit transform. Yeah, I really do need to look that up. I know this is pretty crucial. I'm going to make a note to read about that before next time. All right, but yeah, for the time being, let's just go ahead and standardize our values as such. And now we should be ready to feed our data into the neural network, which is going to be very cool. All right, so let's go ahead and import from tensorflow.keras.models, import sequential. Now, you might be wondering, what is TensorFlow and Keras? TensorFlow is a very, very powerful deep learning library. It's the library that you create all your neural networks in. Not all of them. There are a couple other libraries. It's the most popular one. I think it's developed and maintained by Google, I think. And then inside of it, we have Keras. Now, Keras, all that Keras does is it makes our life a little bit easier. It was developed by a pretty popular programmer. I think he worked at either Google or Facebook, I forgot. And what he did is he created the Keras library. Initially, the Keras library was built on top of TensorFlow, and it just made life easier. And with the most recent version of it, TensorFlow actually now incorporates Keras, so that's why we import them together. Before we would just do from Keras, it would be like a separate library, like how we do import Seaborn, like separately, even though it's built on top of Matplotlib. But now they're together, and we use Keras to build very clean models. Once you get very like complicated into neural networks, you start just using TensorFlow, which is a little bit more flexible.
But what exactly does Keras do?
It basically, it's a deep learning library. It creates our neural network. We'll create a sequential neural network model, and we're about to import the layers, I guess. So who remembers what the layer where every input is connected to every output, what layer is that called?
Wait, can you repeat the question?
Yeah, we had like a specific type of layer inside of a neural network that was characterized by every input connecting to every output of that neural network.
Dense layer?
Yeah, dense layer, a densely connected layer. So from tensorflow.keras.layers, awesome. And we're just going to import dense. So that's a type of neural network layer. And you might be wondering what sequential means. It simply means that it's a model where when we create it, we just specify one layer after the other. So yeah, pretty straightforward, to be honest. Yeah. All right, so let's go ahead and look at the shape of our training data, right? Because remember, when we're creating a neural network, we always need to know the shape of our input data in order to specify the number of neurons that we have on the first layer, right? Otherwise, the model doesn't pick up on that itself. So it looks like we have 15,129 by 19. So it looks like we have 19 features like square footage, condition, grade, it has a waterfront, so on and so forth. It looks like we have 19 of those features that we're going to use to determine our price. And just for consistency's sake, you want to check on your test data as well. Let's do xtestdata.shape. And yeah, so it looks like it's by 19 as well. Why is this smaller? Why is this number smaller?
It's only 30%.
Because it's 30%.
Yeah, exactly. This is only 30%. If you wanted to do the math, you can, but just trust that the model split it correctly. But yeah, this 6,500-ish is just 30% of our data. And so that shows us how we're going to train on a lot more data, and then we're going to test to 6,484 unlabeled data points. All right, let's start creating the model. So whenever we create a model, the first thing that we need to do is specify the type of model. Now, sequential models just mean we're going to specify one layer after the other. In my research, I've only created sequential models. I'm actually unfamiliar with other types of models. but I'm sure they're out there, and I'm sure they're used in a lot more complicated scenarios than what I've experienced. But model equals sequential is very standard. Now what we can do is add our different layers. And the way that we do that is, since we have a sequential model, it's almost like a list, right? Sequential means something that's like in an ordered fashion, right? A sequence of events, something like that. And all we have to do is just keep adding our layers one after the other. Now, what was the definition of a deep neural network?
Multiple of the gray
Two-
areas.
Yeah,
Yeah,
two or more
Multiple hidden layers.
yeah, two or more hidden layers, right? So at our very beginning, what was the first layer called? Hidden layers
Input.
are in the middle. What?
The input.
Yeah, the input layer. And then we have the input layer, we have all the hidden layers, and then we have the output layer. So the hidden layer, let's actually take a look back at our diagram from the slides. The hidden layer looked something like this, right? So this hidden layer had this input layer had 1, 2, 3, 4, 5 different types of inputs. However, how many inputs do we have in our example?
19.
19. Great. So what we need to do is we actually need to create a dense layer with 19 in the very beginning. Now, this is the absolute hardest part of creating neural networks, is basically working with the size of the data. It's something that takes even myself, who's created dozens of neural networks by now. It's hard to remember. We're going to say activation equals ReLU, and we're going to learn about what this means afterwards. I just wanted to get through this example right now, especially since we're an hour into time, actually, going a little slower than I expected, but it's all right. Now, what I want to do is create a deep neural network. So we have our input layer, but I want a bunch of dense layers in between. So just copy and paste that dense line, and let's just have 4 of them. Now, the more of these that you have, the more deep your model is, and the more complex it'll be able to do. But what is a fear that we have if we make it too dense?
Overfitting?
Yeah, overfitting, right? That's a fear that we should have if we overcomplicate our model. So for the time being, since this data isn't the best, right, it's pretty hard to predict house prices. We'll just create a simple model and see if we're at least kind of sort of correct. All right.
Wait,
And now,
so the first modeler add dense 19, like all that stuff. So is that the input layer, and then every layer after that is just a hidden layer?
yeah, every layer after that is just a hidden layer. And if we were to think about what this model looks like, it would basically be kind of like a square model, right? A 19×4 model. We have 19 columns or 19 neurons that are densely connected to 19 neurons. And wow, that would be a lot of lines, right? If every single of those 19 neurons was connected to another 19 neurons, man, that would be a lot of connections, right? We've already gotten into a pretty dense neural network, and we're just scratching the surface. And so let's think about what the output layer is. So the output layer is, what is the output layer spitting out, I guess? What do we want it to spit out?
The estimated price?
Yeah, the estimate of the price. So we need one final dense layer, so we can paste that in, but it's not going to be 19, right? We don't want 19 things to spit out of our model. How many things do we want out of our model?
1.
1, perfect. We want one price, and this is the most crucial step inside of a neural network, is the final layer. Well, the beginning layer and the final layer is the most crucial step to understand. And it's something that if there's one goal that I have for this intro class, is to understand how to format the final and the initial layers. And then in between is something that you'll learn simply with experience. You'll simply learn how to figure out with experience. And there's not going to be an activation here. We'll learn about what activation means today. But yeah, just go ahead and delete that. So dense 1 means a final one dense layer, right? So we can kind of visualize this. Actually, I'll go ahead and draw out what our neural network looks like, because I think it's pretty cool. Let's see. Did I select that?
By removing the activation, what does that do?
We'll learn about what activation means in a second, but in regression, you don't need an activation for the final layer, basically. But yeah, so let's imagine that we had 4 instead of 19, because I'm not going to draw out 19 things, unfortunately. So we have 4. This is tough. We have 4.
Wait, Arush asked a question in the deep learning discussion.
Oh, I've missed it. Thanks for letting me know. Arush asked, how do you decide how many layers you should put with a lot of different types of models? There's not an answer for that question, and even the most seasoned deep learning researcher would not be able to give you an answer to that question, simply because there is no answer that really exists. It depends on your data. It depends on the format of your data, whether it's tabular data or image data. It depends on how complex your data set is, whether you're dealing with large images. Medical images require very deep neural networks because they have to pick up on a small amount of things. But honestly, it comes down to you're able to develop something that's kind of rough once you get more experienced with working with different types of data sets. And then after that, it's just a little bit of fine tuning. You try to implement things that try to avoid overfitting, try to increase the accuracy, and so on and so forth. So it becomes a lot of not really trial and error, but you look at what went wrong and you start to develop an intuition for how you can kind of approach to fix it, if that makes sense. But yeah. Let's take a look at this neural network. And yeah, unfortunately, it's not a very satisfying answer. But yeah. Every day on if any of you use Reddit, sorry.
Yeah.
Every day on Reddit, people are always asking, like, how many layers should my model have, and so on and so forth on the machine learning subreddit. There's no answer for it. All right. So we have something like this, and simply enough, all that we're doing is these are densely connected, right? So each of these yellow points is connected to each one of the following yellow points. You get the idea. I'll just draw 2 of them. Right, so we have something like this. It's gonna look like a whole big web. And then at the very end, we still have a dense layer, but they're all connected to one output. And the reason that they're connected to one output is because we simply want one price out of it, right? Let's say we had a data set and we were trying to detect whether it was a cat, dog, giraffe, or horse. We would need 4 in the final layer, right? Because there's 4 possibilities. There's 4 neurons that we would need at the very end that it could possibly be. So hopefully this makes sense. This architecture makes sense. This is called neural network architecture. All right, I will close this annotation tool. And the last thing that we need to do is compile the model, basically. It's just called model.compile. And we have to specify an optimizer. Unfortunately, because of you guys' math background, I will not be going over optimizers in this class. Yeah, unfortunately. But yeah, an optimizer is basically telling the model how to optimize itself. There's different types of optimizers, and Adam is a very safe bet. It works for a lot of different types of situations. And the loss, remember how we did like mean absolute error and so on? This is just mean squared error, right? So we're just going to use this as our error metric for our model. Yeah. Go ahead, and after this, let's do something that takes a little bit of a look at our model. We can call model.summary to see what we ended up with. Oops. Did I do that wrong?
The model has not yet been built. Build the model first by calling build.
Yeah.
Or calling fit with some data. Or
yeah, I guess we have to do model.fit first. Yeah, that's no issue. Just delete that line and compile the model. We'll look at the model summary after training, I guess. That's strange. Maybe it's different for this type of model. You're usually able to call model.summary right after.
I have a error in compile on line 9.
On line 9. What does it say?
Invalid keyword arguments in compile and then optimizer. I think I spelled it wrong.
Yeah, make sure it's ADAM, which stands for like adaptive. I forgot adaptive what? Let me look it up. Atom optimizer.
No, I spelled optimizer wrong.
Okay.
All right, I'm ready.
All right, cool. I forgot what it's called, but it basically adapts some sort of learning rate for those that learn about what that is later on. But yeah, let's go ahead and call model.fit. Model.fit. So this is exactly like reg.fit or whatever when we were doing that earlier. And we want to fit using our training data, right? This is the training process. We want to do y equals y train. And we can also pass in some validation data to make sure our model is not overfitting, right? So what we do is we do validation data. Remember, this is all in the same line. All I simply did was press enter after this quotation mark so that I'm not having like a super like wide line of code, if that makes sense. It's very neat to do your code on separate lines like this, but it's all in the same function. Validation data equals, and what is our validation data? Well, it's X test and Y test, right? We want to use that. That should be a lowercase t. And now what we're doing is we're going to specify the batch size. So if you weren't in the intro to Python, then what this is basically doing is similar to kind of, I guess I can kind of compare it to a generator function where we're going to load 128 data points into memory at a time. So we're going to train on batches of 128 data points. So we'll do 128 data points, take a look at the validation, then feed in another 128, and so on and so forth. So that's what the batch size is. A lower batch size will give you more accuracy, but it'll take a longer time to train, and a higher batch size will give you less accuracy, but it'll be faster. You got to find a sweet spot by just really toying around with the batch size. And yes, a longer train time can make a difference. The neural networks that I was creating for my science fair, they took up to 32 hours to train. So yeah, imagine one time I was like playing around with the learning rate, and the learning rate is basically telling it like when to learn. And I accidentally put 0.01 instead of 0.001. And I couldn't find the error for forever. And every day I would just change the batch size, or not even every day, right? 32 hours is more than a day. And I was just off by 1 0. And I spent like hundreds of hours like waiting for the training to finish simply to, yeah, I don't know. It was a very sad, that was a tangent, but it was very sad. Here we have epochs. Remember, epochs are iterations through our data set. So it's the number of times we're going to kind of cycle through all of the data that we're working with.
400 times.
Yeah, 400 times. But all of these take under a second to run. So even though it's 400 times, it's going to be extremely fast.
Could you explain the batch size again?
Yeah, batch size is how many data points we're loading into RAM at one point in time. So we're going to train on 128 at first. We're going to basically split our data set into sections of 128. So how many data points did we have in XTrain? Where is XTrain? XTrain, we have 15,129, right? So what we're going to do is we can simply do 15,129 divided by 128. So if I do 15,000 divided by 128, it looks like we're going to have 119 batches, if that makes sense. It's like a cluster of 128 images that we do at a time, basically. Yeah. Again, I keep using the bread analogy, but it's like 119 slices of bread that are 128 thick. I don't know why I keep using that analogy. It's not even that good. But yeah, let's go ahead and run it. You'll see the batch size, and this should go in rapid fire mode.
Wait,
That's pretty cool.
what exactly are the epochs again?
Epochs is your iterations through the data set. But yeah,
Wait,
what year?
so what
Mhm.
does the 119 like? Yeah, I see the epochs and then the
Yeah, the 119 is the batch. So if you do 15,000, which was the size of our data set, right, divided by 128, which was our batch size, it gives you 118.8 or something, which is close to 119, right?
Wait, what happens if you have a higher
okay.
epoch?
What?
Like, what happens if you have a higher or lower epoch?
So epoch was
Please show
our
the code again.
Yeah,
Oops.
1 second. Let me show what an epoch is. Epoch is this graph. So as epoch gets bigger, we hope that our error gets smaller. Epoch is like your training time or your iteration through the data set. So the longer you train, the lower you want it to go, right? Epoch is basically specifying how long you want to keep training for.
Let's go. My ping is 2.
What?
How do
Oh
you
no, wait, what is
determine
the
that?
2 MS?
Let me scroll up. This is very long, unfortunately. Yeah, here you go.
Validation.
And it'll take a minute or two to run, but it should be pretty fast.
So wait, exactly how do you determine how many epochs you want?
You just try a bunch of them out, and then you see if you do 2 less epochs, then that means your model was still decreasing, but you cut it off too early. So you would want to increase the epochs. Oftentimes, you just do a bunch of epochs, and we'll learn how to make the model stop automatically when it starts to overfit. So we'll learn how to do that. But I've tested 400 epochs, and it works well. So we'll just run with that for now.
So what does like the loss, like I know we did a root squared or a mean squared error. So
Yeah.
what does like it says loss and then the validation loss?
Yeah, so the loss is actually just the mean squared error after every iteration through the data set. So ideally, right, if we're looking back at our graph, are you good with the code, Noah?
No, I have an error. I posted on the.
Oh, okay, let me take a look.
Make sure you're putting commas after them because that's what I forgot to do.
Yeah, you missed
Oh.
a comma after Y train. This is all inside of the same function.
Yeah, that's
but
exactly what I did. That's the exact error I had.
You're good. It's
Thank you.
I miss that comma as well all the time. But yeah, what you just witnessed was your model learning from the data. You literally witnessed the model going through all of the data and creating its weights and biases by itself. So Shreyas had asked me a couple days before the class started, what does it mean? Do you manually train a model? Well, I guess not really, right? We just specified what the model looks like. We specified our architecture. We specified our model architecture, and we simply just call model.fit, and it just does its thing, right? And we just watch it go. These equal sign, by the way, they were really fast because this data is easy to read. But usually it's like an arrow, and it's like a loading bar. So these just show full loading bars, and it just shows the progress that's going on. You literally witnessed your model learning on a bunch of data. That's what's going on right now. So very,
Rise,
very
my
cool.
child, rise.
And going back to Shree's question about loss, the loss is the mean squared error, right? So mean squared error, we learned about that in the research class. And ideally, as your epochs go on, remember if we're looking back at this slide, as your epochs go on, you want your error metric to reduce, right? You want your model to be better. You want it to have lower error as we go on. And also, when we want to not overfit, we want our training set and our validation loss, our training loss and our validation loss to be very, very similar. So these are huge numbers, right? The model sucks at this point. It's absolutely horrible. But hey, it's not overfitting by that much, which is a good sign. Let's scroll all the way down to 400. It still has a huge loss. So this neural network seems to be not very good at predicting house prices, but it might be decent enough. Let's go ahead and plot our losses to see if yeah.
Are we supposed to have the same number?
Yes. No, well, no, you shouldn't have the same exact number for this. That's because a model A neural network initializes its weights randomly, if you remember me talking about that, and then it adjusts it. It should be similar, but it shouldn't be the same.
Okay, yeah, mine's like the first 3 digits are 291.
Okay, yeah. So they should be similar, but not the same, simply because a neural network initializes its models or its weights randomly, which is the crazy part about neural networks, is that it starts out completely random, and then it starts adjusting the weights and biases to be better, I guess. So let's go ahead and plot these losses on a graph to see if we can come up with something like I had on my slide. So the losses are stored well, we want to read them in data frame format. They're stored in something called model.history, which is basically a data frame of loss and validation loss. And sometimes it's accuracy too. Like you can monitor different things. We'll learn how to do that. And let's do losses.head to see if we've done this right. And yeah, looks like we have loss and validation loss. Now we can simply call losses.plot and see if the neural network did a good job.
I think it did.
Yeah, it did. It did an amazing job. You can actually almost not even see the blue. Let's actually make this, yeah, we can make this bigger. plt.figure fig size equals 12/8. And let's actually increase the DPI as well. DPI equals 250 just to get a nice clear plot.
Wait, can you scroll up again?
Yeah, that seemed to do absolutely nothing, probably because it's the pandas.plot function. No dice with this one. Let's delete that.
I forgot what DPI is again.
DPI is dots per inch. It's like the clarity of the image.
Oh.
Unfortunately, it doesn't seem to work on pandas plots, so you can just delete that line. Is there like a fig size argument inside of here? Let me see.
Fig size pandas plot.
Yes, there's a fig size inside of here. I think we can do fig size equals 12/8. By the way, if you want to look at the keyword arguments, just hover over the plot command for a second, and it'll pull up this little helpful string, and then you can just kind of flip through some of these and see what you want. It's pretty useful.
Oh, that's cool.
Yeah. And maybe let's keep our fingers crossed. Maybe we can just pass DPI into here. I don't know. Nope, DPI is not. Okay, never mind. Delete DPI, keep fig size. And there you have it. You have made your first loss plot that's monitoring how well your model did on predicting a house price. So if you look, we started out with high error. And by the way, note how they're blue and orange, by the way. This is important. And did the model overfit?
No.
Nope, almost not at all. This is actually freakishly good. And the loss decreased almost towards 0. Remember, loss is looking at the error. So we did a pretty good job, to be honest. Even though the mean squared error was quite high, the model seemed to learn very well, but it seems that it was off by a certain percentage, if that makes sense. So, oh man, we've spent like an hour and a half on this example. This was not accounted for. Okay, I'm gonna go the full 2 hours again today. sklearn.metrics. Let's go ahead and import our couple of things. Let's import mean squared error. Wait, do we need this? Let's just look at mean absolute error for the sake of time. Mean absolute error. I know you guys can definitely do the other ones on your own. And let's look at R² score as well, because that's pretty important. Let's import these two things.
Wait, so is R2 the accuracy again?
R2 is the correlation coefficient, R². It's R², but it's denoted as R2 score. But yeah, it's R². It's just written awfully. So let's go ahead and create our predictions, right? The predictions is basically the model creating its own predictions based on unlabeled X-test data, right? Unlabeled X-test data. We're creating predictions with no hints whatsoever. We've trained a model, and now we're predicting on brand new data points. Run that. And let's go ahead and print out a couple of predictions. Let's print out the first 5 predictions. So it's an array, so you can do :5, right, to print out the first 5 predictions. And here we have a couple of predictions. It looks like the first house, it thought it was around 503,000. Yours should be different, by the way, but kind of similar. 647. All right, looks like it's predicting pretty reasonable house prices, right? Remember when we looked at the data, our mean was around 540,000, and it looks like we have some houses that are kind of sort of in that range. Let's go ahead and look at mean absolute error. So remember, the mean absolute error is simply quantifying the difference between the model's predictions and the actual values of the test set. So what we do is we pass in y-test and we compare it with the predictions of the model. So taking a look at this code, does it now make sense why we have a y-test? I guess what we're doing here, let me explain it one more time, is that we call this model.predict. So the model is basically creating a set of predictions on unlabeled data. However, we do have the labels for that unlabeled data, and those labels are y-test. So what we have now is we have the predictions and we have the truth, right? We have the actual prices, and we can quantify the error between these by simply calling mean absolute error, mean squared error. So does the test set now make a little bit more sense as to what we've done with it?
I'm
I think.
a little confused.
All right, yeah, this is confusing. So
The y-test is the true data, and
yes.
then the x-test is the computer, basically the computer's view of the data.
Yes, and it's the computer's view of the data when given unlabeled data. So x-test was unlabeled data, but the corresponding labels for that, we've basically hidden y-test from the model, and we're like, okay, here's a bunch of unlabeled data, create some predictions on it. And then once the computer's created some predictions on it, we're like, ha, surprise, I actually do have the answers to it. So let's see how you actually did with the correct labels, even though we gave you unlabeled data, if that makes sense. Does that make a little bit more sense? I think Noah understood it.
I got it
yeah.
now.
You got
That
it
second
too?
time.
Okay.
Yeah.
What about you, Aru, Shri? Is that making a little bit more sense?
Can you like explain it one more time?
Yeah, sure. So when we first did our train test split, we organized, so inside of the Y data was all of our prices, right? So that is the dependent variable based on all of our independent test X data set, right? So what we've done here is we've created predictions. Let me just write it out. Created predictions based on unlabeled data. And the reason that it's unlabeled is because it's the X data. Remember, the X data doesn't have the price in it. We dropped the price out of it. So what we've done is told the model to come up with its own predictions on the test set. Remember, it's already trained. We already have a fully trained model, and it's stored inside of model. We have a fully trained model, and we're looking at it on X test data, right? Data that is completely unlabeled and data that it's actually never seen before. So this is brand new data. It's like throwing it out into the real world. So we're creating predictions, and okay, that might be good enough to stop there. However, what we want to do is see if the model's predictions are actually good, if that makes sense. So what we do is take a look at the y-test. Remember that 30% of our labels are stored in y-test, and 30% of our data is stored in x-test, and they're corresponding. So these x-test data points actually match up with the y-test data points, except we've hidden it from the model. So we told the model to create its own predictions on unlabeled data. And then what we can do is we can quantify that data by we actually have the answer key with us. We have the answer key to the test with us, and that's inside of y-test, if that makes sense.
Yeah, okay, that makes sense.
All right, cool.
I have another question. So like, how do you find the accuracy? Is that like in the mean absolute error?
Yeah, so loss is it's not really the inverse of accuracy, but accuracy is from 0 to 100. We'll explore accuracy in this lesson. I'm not going to do it for this one. Accuracy, yeah, we'll talk about accuracy in the slides in a second. But I just wanted to show error so that we're not like throwing every concept all at once in our plot. But yeah, good question. We will look at accuracy in a second.
Wait, this line, this mean underscore absolute error,
yeah,
y-test predictions, is that finding the mean absolute error between the y-test and the predictions?
Yep. Yeah, exactly. So that's why we have this line, right? Because the predictions is basically like, it's like the model has generated its own labels, right? That's what the predictions means. And we're comparing the model's labels to the labels that are actually like correct, like the actual price of the house from our data set. Does that make sense?
Mm-hmm.
All right.
I
cool.
was just confirming that.
Yeah. All right. So let's go ahead and do R squared score. And remember, whenever we're doing error metrics, we pass in the same two things, y-test and predictions, because we're simply comparing our model's predictions to what was actually the case in our situation. And it looks like we have an R squared value of around 80%, actually not too bad. So it looks like the model's predictions were about 20% off. And that's actually very interesting. Remember, what was the rough mean of all of the houses? What was the rough, like where were
500K?
Yeah, 500K. So, and our model was off by about 20%, right? So if we do 0.2 times 500K, this should be a star, times 500,000, right? Look, it's 100,000, and look at our mean absolute error. That's very close to that value, right? So it looks like a lot of our predictions are about $100,000 off. So in the real world, you wouldn't want to use this model, right? It kind of sucks. Like, you don't want a neural network predicting a house price that's $100,000 off. So it's not the best model, but hey, it had no overfitting and it had a decent R squared score. And it was a proof of concept to show that, hey, our model can do pretty well, even given some really, really weird parts of our data set, right? So thinking about what we can do to improve this model, what are some of your guys' thoughts? How can we make this a little bit more accurate than $100,000 off? Think back to everything we did in this, I guess, in the code.
Do we train it again?
Yeah, we could train it again, and we could train it again. Well, actually, training it again will yield similar results. Training it again, we might want to train it for a longer period of time, more than 400 epochs.
More epochs.
Yeah, more epochs. But to be honest, right, if we're looking at our loss plot, it kind of plateaued out. It doesn't look like it's going to get much lower than this, right? It's pretty decent already. And we might run into overfitting if we train for too long, right? So what are some other things we can try?
We could try removing more of the data that doesn't affect the price as much.
Yeah, very, very good answer. That's what I was getting at, actually. So if you remember, we looked at the correlation plot. We could actually just take maybe the top 5 most correlated features and just train the model on those. I actually encourage you to do that on your own time. If you do that, what do you have to change inside of the model if you drop more of those features?
When the 19 value, we would have to change it to the new amount of value columns we're actually using. Yeah, exactly. But dense 1 would stay the same, but the others would change, right?
Wait, so if you did only if you only did the top 5 correlated things, would you do dense and then it would be 5? Yeah, it would be dense 5 because you would have 5 input neurons, right? You would have 5 input neurons that are going into the hidden layers. So yes, great. Looks like you guys are really catching on. And another thing you can do, which is not as important and probably won't make as big of a difference as the correlation. The correlation thing will probably be very good. That was a good answer. That's what I was getting at. But you could also decrease the batch size. Might take longer to train, but the model might be a little bit better if you do that. But probably it'll be pretty marginal, to be honest. But yeah, these are all things that you can, as deep learning researchers, things that you test when you're trying to fine tune a model. But yeah, I had a little bit more code planned for this, such as putting in our own test house. We put in the price, the bedrooms, the bathrooms, the living, and see what the model predicts the price would be. But
For the sake of time, we're going to do that with other examples, so you'll learn how to do that, but I'm going to skip that for now, simply because I do want to get through all the classification slides and we're running low on time. But I'll be sending you the code, so you can just take a look at that honestly and try it out on your own. And I'll upload the videos from yesterday's lesson today, probably, and also today's lesson. Yeah. All right, let's take a look at this. All right, let's go back to our slides. So where did we leave off yesterday? We left off on regression. Actually, I'll run a poll. I'll run a poll to see if you got everything working. Did you get the regression activity completed? And is everything starting to make sense? And I hope you see a lot of the connection between the theoretical stuff that we covered yesterday in the slides and what we actually implemented in code. To be honest, the code and the syntax is the easy part, but understanding what's going on, how to interpret these graphs, how to design our input layers to have the right number or the right size, and the output layer to have the right size as well, that's the tough part, right? Writing up the code is easy in my opinion, and maybe it's not that easy for you now, but the more you do it, like it just gets easier and easier every single time, to be honest. And after you do 3 or 4 projects, it'll, like, you won't even need to look up the documentation. It gets very simple. But also the example that we just did was a very, very simple neural network with just 3 hidden layers in it. So they do get far more complicated than that. All right, so let's finish off with our slides on classification. And next time we will create a neural network that can predict handwritten digits, like numbers drawn by people, and it'll be a neural network that can convert that into text, basically, which will be cool. It's the classic. People call it the hello world of deep learning, is to create a handwritten digit detection algorithm. All right, we are done with that. And now let's look at classification. So when we're looking at classification, remember classification can only have 2 possible results, right? It's not like regression, where regression was like we could measure our mean absolute error as $100,000, right? We could measure our R-squared score as 20% off. But inside of classification, it's a binary result, right? It's either you're correct or you're incorrect, right? Only 2 possible results. There's only 2 possible outcomes that it could have. And that makes life sometimes actually a little bit easier and a little bit more interesting, and I'll show you why. So let's talk about what classification really means, I guess. Let's start with, I guess, looking back at kind of a pipeline, but let's look at an image recognition classification model. So let's say we have a pre-trained model, and that's stored in this light purple thing over here. This model has already been trained on the training set. Now what we do is, actually this might really make a lot more sense. Yeah, this might actually make this a lot more easier to understand. What we do is we have X test and Y test. Remember, like 30% of our images, let's say 30% of our images are in X test and 30% of the corresponding labels are in Y test. So now what we do is we take that image from X test and we put it into the trained model, right? We put it into the trained model, and the trained model spits out a classification. Hey, it thinks it's a dog. So now simply what we have to do in classification is we just have to compare it with the correct label from Y test. And if dog equals dog, right? If the prediction equals the truth, it's called the ground truth, or the correct label and the ground truth mean the same thing. If the prediction and the ground truth are the same, then hey, our model did good, right? Our model did good, and hence we can move on. Okay, does this process kind of make sense? And maybe now the part where we did the mean squared error in the last, or the mean absolute error in the last example, maybe now that makes sense. This was our predictions, and this was our Y test, and we performed mean absolute error on our predictions and our Y test. It was simply comparing the predictions created by the model on a input image with the actual true labels, if that makes sense. All right. Yeah, and let's say we were training a cat-dog classifier, and it took this image and it said it was a cat, and then dog not equal to cat, right? That's stupid. So our error would be high for this one, right? Because it's an incorrect classification. Dog, and hopefully you remember this from Python, the exclamation mark and the equal to sign means not equal to. So this is really boiling down what is going on with a neural network in just a couple steps. All right, and then she was asking about accuracy. Let's talk about what that is right now. So accuracy, it's just like the grade on your test, right? It's simply like the number you get right divided by the total number of questions on the test, right? If it's a 100-question test and you get 94 of them correct, you get a 94% on your test, right? Pretty easy, number correct versus total number. Hopefully this formula makes sense. If you want to write it down, be my guest. But yeah, it's just a standard accuracy formula just used in everyday life. So let's talk about why accuracy is not always a good metric, right? You might think that, hey, like my model is like 99% accurate. That means like wow, it's doing pretty good. But it does not perform well with unbalanced classes. And classes, again, remember, classes refers to like our types of classification. So if we were training our cat and dog classifier, we have two classes. The first class is cat and the second class is dog. And so on and so forth. If we had multiple classes, we can have more than two classes. Well, let's say we had 99 dog images and one cat image. If our model always predicted dog, it would be 99% accurate, even though it had no idea how to detect a cat, right? So that's extremely, extremely misleading. And actually, when I was doing my first deep learning project, I was like, oh wow, my neural network is like 80% accurate on these images right off the bat. Like, man, I really got it on my first try. But that's because like I was looking at medical images, and actually all it did, 80% of the data set was just images of healthy people. And so all it did was it regardless of if they were diseased or not diseased, it just said that everyone was healthy, and it achieved an 80% accuracy. And the model thought it was OP, right? It just like right off the bat, it was just so good. And I was like, wow, the model is really good right off the bat. And then I realized that, well, 80% of the patients were healthy, and the model just predicted everyone as healthy. And as a result, it achieved a reasonable accuracy. So that's kind of stupid, right? And you can understand how accuracy is a very misleading metric in this case. If we had 99 dog images and one cat image, it's 99% accurate. Even if it like has no idea what a cat is, right? It could just get that one wrong on purpose and just say everything was a dog and be pretty accurate. This is an extreme example, obviously. Even if it's like 70 dog images and 30 cat images, and it just detected all of them as dog, it would be 70% accurate, right? And yet it has no idea how to detect what a dog is. And hence, we will look at more informative metrics and better metrics than simply like accuracy. Accuracy is a very basic metric. You still do it, but it kind of sucks when you have unbalanced classes. If you have balanced classes, it's very good. Like if we had 50 dog images and 50 cat images, like by all means, go for accuracy. It's a pretty good metric in that case.
Wait, I just thought of something.
Yeah.
So is AI, like, are these like neural networks with all this like accuracy? Is this how like autocorrect on like devices works? Like they'll train a program to detect what like letters go to create what certain words, and like based on what someone's typing, they can predict which words are most likely the outcome.
Yep, exactly. That's yeah. There's a neural network that's been trained for autocomplete, or actually a couple neural networks that have been what's known as ensembled together, which means to take a bunch of neural networks and like almost like smash them together. And they're created by big companies. There's entire companies where all they do is make autocorrect or autocomplete software, right? There's autocorrect that fixes typos, and there's autocomplete where that if you have an iPhone, it actually like guesses the next word in the sentence, right? That's a combination of natural language processing and something known as like, I think it's like recurrent neural networks and long short-term memory units, where it's basically able to take like the past 5 words of your sentence, and based on those past 5 words, predict the next sentence. And that's another branch of like deep learning. Well, we're in this class, we're actually going to focus mainly on computer vision. But yeah, another branch of deep learning is like text processing. I've never done any research in it, and I'm looking forward to taking some classes on natural language processing and stuff like that. There's actually something where you can combine computer vision and natural language processing, where you take an image and then based on the image, you generate a caption for it. My friend actually, like, he was teaching, I was teaching another CS camp, not related to Coding Kickstart, and one of his lessons was about that, which was super cool. It was like a cheetah, like it was like a picture of a cheetah, like in mid like leap, and the natural language processing, not only did it figure out that there was a cheetah in the image, but it also figured out that the cheetah was running like in the image. So it was a combination of detecting what's in the image and also creating a sentence out of it. So it's like a combination of two almost unrelated, well, they're related, but two fields that require completely different sets of code, which I think is very, very interesting. But yeah, great question. So what is this? I don't know why I had this slide. Oh yeah, I do know why I had this slide. So looking back at our deep neural network, this is what we're now working with. So we're going to work with image classification in our case. So image classification, now let's really, really think about what our inputs and our outputs are. So what do you think, let's say I had a data set of, I don't know, let's just do a simple cat-dog classifier to start out with. We're doing a cat-dog classifier. What is our input size? This is a trick question. It might not be intuitive.
Our input size would be 1, right?
It's not 1, and so we have cats and dogs. It's actually, so inside of the image, when we're creating a deep neural network, so remember inside of our tabular data, we had 19 different features inside of the data set, right? There were 19 different variables, I guess, that we were looking at. However, when we're dealing with cat and dog images, what are our features?
It's unlimited until we like classify them, right?
What do you mean by that?
Meaning like there could be an infinite number of things we're looking for in the image, and that, like, it's based on what we want to look for in the image.
That's a very good thought process. Very good thought process. You're kind of, I would say you're like kind of sort of correct in a way, but there's a finite number of features. Sure, there's an infinite number of features for the model, but there's a finite number of input data that we can pass in. How do we measure the input data when we're dealing with images? Think back to the last lesson of Python for research.
Color?
Color is a good guess. Not quite. What is an image? What is an image?
Pixels.
Yeah, pixels. So if we have a data set of images, right, we can detect as many features as we want, or the neural network can detect as many features as it wants, but it's constricted by the number of pixels in the image, right? You can't go below a pixel. So that is actually the fundamental part of the input level of our neural network. It's actually going to be the number of pixels in the image. So our first layer inside of what's known as a convolutional neural network, a convolutional neural network is used for image processing. Our input is going to be dictated by the number of pixels in the image. And now you might ask that, hey, what the heck happens if we have different, like a data set where the cat images or certain cat images are larger or smaller? So do you think we can feed in different sized images to a neural network? Do you think that's possible? Intuitively?
Yes, but you would need to like resize them, right?
So yeah, your answer is correct. So the answer is no, because you would need to resize them to be all the same size. Yeah, yeah, you're on the right track.
Resize them, would it just like skew the data?
Yeah, you would have to resize them, and we'll actually usually you try to find like the mean of all the like widths and lengths, and then you resize them to that. But there's certain neural networks that require a certain input dimension. We'll learn all about that in our lesson about convolutional neural networks next time. But for our case, we will simply think about it as everything needs to be resized. So there's two ways you can resize an image, right? The first way is to just like squish it vertically or horizontally. What's the second way you can resize an image?
Proportionally.
Proportionally, that's a good answer as well.
Oh, I forgot what it was called, what we did in one of our last Python for Research Network lessons, where we like, it was like, you explained how you used it in your science fair. I might be completely off, but like how you could zoom in and like reduce the pixels and then like redistribute the pixels again.
Oh yeah, image morphology. No, you don't need to do that. No, not quite. But that is something that you can do actually before feeding in your data into a neural network. That's why I was actually teaching that stuff, is because you can actually take an eroded image and then feed the eroded image or a dilated image or an edge detected image into a neural network. Yeah, good guess. Any other ideas how we can reduce the size of an image? Think about the Photos app on your phone.
I mean, zooming in and zooming out.
Yeah, you could zoom in.
Photo.
That's the only thing.
What'd you say, Noah?
Crop?
You could shrink a photo.
Yeah, you could shrink, and yeah, you can just crop the photo, right? And oftentimes cropping is pretty good because like some photos have like a frame around it, and you want to get rid of it. Or like a lot of times when there's medical images, oftentimes there's like devices in the background, or like there's like a ruler like trying to measure like the length of it, and like you don't want to feed in the ruler into your neural network, right? That would just confuse the neural network a lot. It would be like what the heck is this? Like, looks so strange. I don't know, maybe this is just a cancer, and it would just look at the ruler and it would just say this is a cancer. And you don't want that to happen, right? I've had that many a times. Like when I was looking at skin cancer, doctors would put these two like stickers next to it. And when I performed some sort of analysis on the neural network, I was like, why is the neural network looking at all these healthy images as cancers? And I realized it was just highlighting this neon green sticker that a lot of doctors put, and it was like this is a cancer right here. And I was like, wow, thanks. And I had to crop all those out. It took forever, but it's a necessary part of feeding in your proper data, right? All right, with our last couple of minutes, let's talk about activation functions. If you remember, we use activation equals ReLU, ReLU in our when we were creating our neural networks. Let's talk about activation functions. So in binary classification, our output can either be 0 or 1, right? So let's say we're making a cat and dog classifier. We could just say that cats are 0s and dogs are 1s, right? Because again, we have to what's known as encode the final answer into just a 0 and a 1. And in binary classification, that's pretty easy, right? 0 is one of the classes and 1 is the other class. So our output is no longer a price or a continuous value. It's simply a category, and a category is marked by a 0 or a 1. All right, hope that makes sense. So the very first simple activation function, remember a function, think back to algebra and graphing and so on. Simple neural networks can use what's known as a step function. And a step function, can you guys see the blue on the step function over here? Is that visible in the stream? Yeah. Okay. Yeah, but basically a step function just looks like a stair step, right? It's 0 everywhere below, everywhere in the negative region, and it's 1 everywhere in the positive region, right? So you'll I don't know if you guys have learned about step functions in math before, but yeah, this is what a step function looks like. Just looks like a stair step. And from negative infinity all the way to 0, it's just 0. And from 0 to positive infinity, it's just 1. However, we usually don't use a step activation function simply because there's an immediate cutoff between 0 and 1, right? There's no shades of gray in between our two very extreme cutoffs. And oftentimes when you're doing classification, there's like, to a neural network, right, there might be a small dog that kind of looks like a cat. And I don't know, that sounds really strange, but to the neural network, there might be a cat that looks kind of like a dog or vice versa. It does not reflect small changes, and hence it's kind of bad. But this is the first type of activation function. The best activation function is what's known as a sigmoid function, and it's used oftentimes in the last layer of a neural network. Remember in the regression, we had no activation function in the last layer, but when we're dealing with some new ones, we're going to be using a sigmoid function in the last layer. So it kind of looks like a step function, right? It looks like a step function, but it's a lot more subtle. It's shaped like an S. This is called a logarithmic or an S-curve inside of math. You'll learn about it in calculus and why it looks the way it does, but for our purposes, you can just kind of look at it visually and see what's going on, right? So we're passing 0.15, and it looks like greater than 50%, it's a 1, and greater than or less than 50%, it's approaching 0, right? And this might make a little bit more sense to use than the step function, simply because when we're creating a classification, remember I said there's two possible things, 0 and 1. But let's say we had a dog that looks like a cat. Maybe what we would want to do is give it like a percentage of like 60%, right? Where it's kind of leaning towards dog, but it's also kind of right on the cusp between a dog and a cat. And hence we would use a sigmoid function because we can actually put 0.6, right? We can put 0.6 and it would be right around here, right? Right around here. So it's leaning towards the 1 classification, but it's still able to show subtle changes, right? It's sensitive to small changes. However, if we had a dog that was closer looking to a cat than a cat looking closer to a dog, we could do something like 0.4, where it's leaning towards the 0 side, but it is kind of on the cusp, and it's representative of basically kind of giving us a little bit of an insight as to what the model's thinking, right? The model is unsure whether it's a 0 or a 1, but it's somewhere in the middle. So this is very, very important to understand. Yeah, I guess I'll run a poll.
Wait, I'm confused how that works. So
yeah,
something that is similar, like that's more in a gray area between the two, how would the sigmoid function determine which one to assign it to?
So that's the beauty of it. We get to specify as the machine learning researcher. So oftentimes you start out with 50%, right? So let's say we had 0 and 1 on a number line, right? And we had 50% in the middle of it. Or actually, let's do 0 to 100. So it's a percentage from 0 to 100, and we had 50% in the middle of the number line, right? So let's say 100% was dog and 0% is cat, okay? So if it's closer to 0%, it's more likely to be a cat. And if it's closer to 100%, it's closer to be a dog. So a very simple thing is that greater than 50%, mark it as a dog. Less than 50%, mark it as a cat. So does that make sense?
Yeah, but didn't you just say, what if there's a dog that looks like a cat that's around 40%?
Yeah.
So would it label that wrong?
It would label it wrong. It would label it wrong. So if it was
the accuracy of it.
Yeah, it would negatively impact the accuracy of it. But let's say, so dog is at 100%, but let's say it's a dog that looks like a cat, but the model still kind of thinks it's a dog, right? So it would put it at like 55%. However, 55% is still closer to 100%. So even though it gives us a little bit of insight that, hey, the model is kind of confused on this one, but it still classifies it as a dog. If that makes sense, because it's on the right side of the 50% on the number line, if that makes sense. Yeah, that's the best way to explain it.
Yeah, I got it now.
Okay, cool. And for everyone else, I just ran a poll. If it doesn't make sense why we use a sigmoid function. That's not a sentence, but yeah, just hit a thumbs up if you get the essence of it. All right, 4 thumbs up, so we should be good. Oh no, that's 3.
Why does simple poll always do thumbs down?
Because it basically sets like a dummy thumbs up for you to tag your own onto, if that makes sense.
Instead of having to add your own reaction, it adds one for you.
Oh, okay.
Yeah. All right, so now let's look at the ReLU function. The ReLU function is not that hard to understand, I guess. It's basically like anything less than 0, it's just 0. And anything greater than 0, it's the line y equals x, so it's just a linearly straight line. Unfortunately, I can't go more into the math beyond that. Just understand that ReLU performs very well overall inside of neural networks. It has a lot to do with a lot of multivariable calculus and linear algebra. And to be honest, some of which I don't know myself. I haven't taken linear algebra yet, but I do understand the multivariable part of it. But yeah, just think about this as this is what this ReLU function is doing. Anything less than 0 is just 0, and anything greater is just 1. Or it's just like y equals x. So 1 equals 1, 2 equals 2, 3 equals 3, and so on and so forth. So we use this stands for rectified linear unit, and it deals with a major issue inside of neural networks called a vanishing gradient. So that's really why I can't explain the math behind it, is because simply I don't know how to explain a vanishing gradient without explaining a lot of calculus. And sorry, we're a little bit over time, but I will take another 10 minutes of your time. If you have to go, no worries. You can just watch the last couple minutes of this lesson back later. Let's quickly talk about one-hot encoding. Actually, if you do have to leave, please try to stick around for this. This is very important. So one-hot encoding. So remember how I said in binary classes, we only have 0 and 1, right? But let's say we didn't just have cats and dogs. Let's say, I keep using giraffes and horses because that was one of the examples that I wrote up. But let's say we had 4 classes. So how can we have 0 and 1 with 4 different types of things, right? That's kind of confusing. Well, what we can do is something called one-hot encoding. One-hot encoding. One-hot encoding is easy to understand after you understand it the first time. In the very beginning, it's a little complex. So let's just look at this left thing first. So let's say our first data point is the color red, and then our second data point is the color blue, then green, then blue. So what we do inside of one-hot encoding is we create a table of zeros and ones, and we create on this top over here. On the top over here, we have all of the possible classifications, and simply all that we do is we mark a 1 in the correct class, and we put a 0 in all of the other classes. So yeah, just take a look at it. So you see how ID1, right? Our first data point is red. So hence we fill in 1 for red and 0 for blue and green, right? Because ID1 is not blue, it's not green, it's just 1. So by one-hot encoding it, we've represented our entire data set, all of our classifications with just 1s and 0s, right? If we take a look at ID4, it's blue. So that means color red is going to be 0, color blue is going to be 1 because it's blue, and color green is going to be 0. So this is how a neural network makes 0 and 1 classifications using the sigmoid function, even though we only have zeros and ones, right? We have 3 separate colors, yet we're able to represent it with just 2 numbers, if that makes sense. Does one-hot encoding make sense? I'll run a poll, and actually, if someone wants to try to explain it back on mic to see if they understand it, that would be cool as well. If you think you got the hang of it.
So it's like on the left table, since red is 1, so in the right table the correct one would be 1 for the color red. Everything else would be 0.
Yeah, you can kind of imagine it like checks and X's. It's like you're putting a check mark in the red box, and then you're putting X's in the blue and the green box, right?
Wait, so is the reason that the 1 is in color red for ID1, is it because in the left like graph, I guess, the ID1 is red?
Yeah. It's basically it's the classification. So if let's say we had a data set of I guess, or let's just say we had a box of crayons, right? And the box of crayons only contained red, green, and blue crayons in it. So what we can do is draw out a random crayon from the box, and then we would go to this one hot encoded table. We would put a check mark or a 1 in the box that showed that it's red, and we would put a 0 or an X in the other ones, right? Because a red crayon cannot be blue and it cannot be green, right? So we simply put a 1 where it's supposed to be. You can kind of ignore the ID for like, just ignore it. It's pretty redundant. It's just matching the data points to it. But yeah, does that make sense?
Yeah.
Okay, cool. All right, let's move on to putting it all together. So putting it all together, remember we have our input layer, which is the purplish, indigo, whatever color that is. Then we have all of our hidden layers, right? And then we have our output layer. Now, inside of this example, how many neurons is going to be our output layer? Inside of this color example?
3?
Yeah, 3, perfect. And what about in our cat dog example?
2.
Not quite. That's a trick question.
Wait, output?
Yeah.
And the cat dog.
Yeah.
Oh, 1.
Yeah, it's actually just 1 because it's either 0 or it's either 1, right? So
Yeah,
there's only
okay.
2 things that it could be. So the reason that RGB is 3, which Noah got perfectly, is because there's going to be 3 possibilities that it is, right? However, for a binary example, a binary is a little bit different in terms of that it can only be 0 or 1. So hence our last dense layer is actually just going to be dense 1. And the 1 means it's going to output a sigmoid probability between 0 and 1, right? It's just one number. It's just one sigmoid probability ranging from 0 to 1. And the reason that the dog and cat classifier has, or the reason that the RGB has 3 is because what it's going to do is it's not exactly 1, 0, 0. What's going to happen is it's going to be like 0.8, 0.1, 0.1. And hence, since the 0.8 is probably what it's most sure of, it's going to convert the 0.8 to the 1, and it's going to convert the 0.1s to zeros and zeros. Something like this. So basically, it'll take a look at class 1. Let's say class 1 was red, and it's 80% sure that the input was red, so it'll assign a sigmoid probability of 0.8. And then class 2, let's say class 2 was orange. It'll say it's 20% sure it's orange, and then all the other colors, and then maybe what's something that's a little closer to red, like magenta or something, I don't know. And let's say we had magenta and it was 0.3, and what it would do is that it would take all these probabilities, it would look for the largest one, right? The largest one is clearly 0.8, and as a result, it would put the check mark in the red box or the class 1 box. So yeah, that is how a neural network works with activation functions. So I hope activation functions now make sense. When we have sigmoid, remember sigmoid only graphs it from 0 to 1, right? But let's say we wanted to graph sigmoid for multiple different classes, such as the example I just stated over here. We use something called softmax. Softmax is just sigmoid, but it's for non-binary. So when we have binary classification, like dog versus cat, we use sigmoid. And when we have multiple classes, such as red, green, blue, or dog, cat, horse, pig, chicken, whatever, like many animals, we would use softmax. And it's just a keyword that you put in the last thing. And what it does is it outputs a sigmoid probability for everything. So here's dog, cat, horse, giraffe. So here's an example output for sigmoid. So for this input image, what do you think the neural network will put for the 1 in the 1 hot encoding? Any ideas? What do you think the neural network, if we were to 1 hot encode this, let's actually 1 hot encode it together. What do you think the 1 hot encoding for this dog, cat, horse, giraffe would look like in a table?
0010.
Yeah, 0010, perfect. So it'd be 0, 0, 0, 1, 0. Very good. All right, and for everyone else that didn't answer it, hopefully that makes sense. If it doesn't, let me know. and I can explain it again. But this is what happens.
Wait, can you explain how it's
So that
how
would be,
to get the 0, 0, 1, 0?
Yeah, sure. What was Noah's question?
That would be horse, correct?
Yes, that would be horse,
Okay.
correct. So basically we would have an input image of a horse, and what it would do is the model would create a set of predictions, and all of these predictions add up to 100% or 1, right? So it would say, okay, I'm 10% sure it's a dog, I'm 10% sure it's a cat, I'm 60% sure it's a horse, and then I'm 20% sure it's a giraffe, right? So what it would do is we basically say that, hey, the model is most sure that it's a horse. So what we're going to do is put a check mark, or we're going to put a 1 in the horse category, and we're going to put a 0 in the dog, cat, and giraffe category. And our final prediction label will be horse, which is our correct prediction. Does that make sense?
Mm-hmm. Wait, so what happens if you have multiple classes? Like, you have dog, cat, horse, giraffe, but like, so you have like 6 other animals, so you have 10 different values.
Yeah.
And if they all have to add up to equal 1, and it's not entirely sure about each one, it's like less than 50% on each one,
yeah.
Would it just take the highest value?
Yeah, it would take the highest value. When you have multi-classifications, it takes the highest value, but when you have binary, it takes less than or greater than 50, like the number line example. That's why we have dense 1. Because dense 1 just plots it on a number line from 0 to 100, and it just takes greater than or less than 50, if that makes sense. But yeah, that's a good question. What?
I don't understand. So I understand, like, the model creates the predictions. That's like, oh, I'm 60% sure it's a horse, right?
Yes.
But then I don't understand what, like, the 0, 0, and then I don't understand what happens when you, like, put the 1 in the horse, like, category.
Well, 1 is yes and 0 is no.
Yeah, one is yes or true, and 0 is false. So this is what one-hot encoding means. One-hot encoding means to represent your final label as either a 0 or 1. So I guess I'll just ask you a series of questions, Shri. So let's say I put in an image of a horse. Is the image of a horse a dog?
No.
No, so we put a 0 in it. Is the image of a horse a cat?
No.
No, so we put another 0. Is the image of a horse a horse?
Yeah.
Yes, and so on and so forth for the giraffe and anything else that we did, right? So all we're doing is we're taking the highest confidence, like the model is most confident that it's probably a horse, so hence we put a 1 there, and then we put a 0 for everything else, because the model's final judgment is that it is a horse, right? Does that make a little more sense now?
Yeah, but so does like, if you one-hot encode it, does it help like future predictions?
This is on the you feed in one-hot encoded data into the model, and then you compare it at the end. So it doesn't affect future predictions, I guess. Yeah.
Oh, okay. Oh, okay. Yeah.
Yeah, it's like the final label. It's like a judge making the final, what is it? Like the final statement or the final jurisdiction on a court case, right? So maybe they were considering, like, maybe he's a little bit guilty, but he had an accomplice. He's very guilty, and he was the main accomplice, or he was not guilty at all. So not guilty at all would have like a 0.0001% thing, while guilty with an accomplice might be 0.3, and guilty without an accomplice might be like 0.6 or 0.7. And as a result, the final jurisdiction, even though there's maybe some dissent in the court, right? Maybe it feels like it might be something else, but it is not as strongly, it doesn't feel as strongly, or presented with the data, it is not as sure that it would be those lower percentage cases. So there can only be one final decision, and that final decision is where the 1 will go, and there will be 0s everywhere else. Does that make sense?
Yeah.
Okay, cool.
Wait, one last question. So the 0.1, 0.1, 0.6, 0.2, those values, are those what the sigmoid function will give you? Those the sigmoid confidence level, pretty much?
Yes, exactly. It's what a sigmoid function gives you, and this can basically be interpreted as 10%, 10%, 60%, and 20%. It's just a range from 0 to 1, and it's some sort of decimal. So actually, this example is not a very good model because it was like 20% sure it was a giraffe and 60% sure it was a horse, right? Those are probably pretty similar to a neural network. Ideally, what we would want is like 0.001%, maybe 0.002 like this. Maybe we would want 2% here, and then we would want like 97.5%, something like this. This shows that a model is very good because a model is very certain on its predictions, and it says that, yeah, these other ones are probably not it, and I'm pretty confident on my answer, right? So this is what a good model would output as its predictions. It still outputs something, but those something should be very low, right? A dog and a cat look nothing like a horse, but a giraffe kind of, sort of. The neck kind of gives it away, but the body is similar, I guess, if you pass in a similar sized image, right? So yeah, hopefully this makes sense. But I will stop here, and you guys are free to go. Hopefully you found this lesson interesting. We will code a digit recognition thing next time, and we will learn about convolutional neural networks and convolution and how image data is fed into a neural network, which is, I think it's much more interesting than regression models, to be honest.
All right. Well, thank you.
No problem.
Have a good day.
You too. And let me know if you guys have questions. I'm just hanging around here for a couple minutes.